Welcome everybody to the third lecture in electromagnetic waves, and today we're going to talk about vector magnetic potential. This lecture is about the mathematical formulation of a very important law in magnetostatic, then a number of applications and exercises, examples on this mathematical formula, which is called Biot-Savart law. The idea behind this is to simplify the mathematical manipulation of the relationship between the magnetic field and J, the source of magnetic field. We know that, like from the postulates of magnetostatic field, divergence of B equals 0. And we said that means there is no individual magnetic charge, like physically no individual magnetic charge. The magnetic charge always in pairs, south pole and north pole. Also we can say this is the meaning behind, like for this law, is the magnetic field lines are closed line. So starting by this one, this law or postulates here, we also like bring into our minds the null identity that is stating that for any vector, the divergence of a curl equals 0. So looking into these two formulas, we can say, okay, we can say B equal curl of A. Why do we do that? It's looking for a simplified or straightforward way to relate B to J. So we need some sort of auxiliary function. This is called the vector auxiliary function, this vector A, and it's called vector magnetic potential. As we saw in electrostatic, we used the voltage, the electric potential V, which is a scalar function, to simplify the solution of some problems. Also, the vector magnetic potential A is used to simplify the solution of a number of problems. So now we defined B equal curl of A, so we can say also like H equal 1 over mu naught curl of A, and this is valid for a linear system that is isotropic, which has like a same property mu, same permeability in all the directions. From Ampere's law, we relate the field to its source, curl of H equal J, or curl of B equal mu J. Anyway, it's the same formula. And now we know that H equal the 1 over mu curl of A. So the relation would be curl of a curl of the vector magnetic potential equal J. So it looks like this introduction of A complicated the problem, but very soon we're going to see how it simplifies like the relationship between the source and the field. Bringing another vector identity about like curl of a vector and its relation to the Laplacian of a vector. This relationship you can sort of like review it from vector algebra. And now we have the Laplacian or nabla square of vector A equal the divergence of the gradient. So the gradient of the divergence of A and curl of A. So putting curl of A into one side, and this we know it's equal from here, curl of A equal mu naught J. So this would be the left hand side. The right hand side would be the gradient of a divergence of A minus nabla square A. So here A is not like uniquely defining B. If you remember the Helmholtz equation or Helmholtz theorem, for a vector to be defined, we need to define its curl and its divergence. So here we just use the divergence of A to define B, and we could prove easily that the relationship between A and B under this definition is not unique. For example, if we introduced another vector A prime that equal A plus the gradient of any scalar function, the curl of A prime also will equal B, because curl of A prime equal curl of A plus curl of the gradient of alpha, and curl of a gradient of any scalar function equals 0. So if curl of A equal B, then curl of any vector of the form A prime equal A plus gradient of any scalar function also will equal B. So here we're just saying that we have a degree of freedom. So actually when we define B as a curl of A, we have like a family of curves that can fulfill this. To simplify the mathematical derivation, we're going to choose just one vector of those family. So this represents a family of curves, and we're going to choose sort of like the condition, and it's called Coulomb's gauge condition, that divergence of A equals 0. So the relationship would be direct relationship between A and the source. And this is actually our goal. Now we have a much simplified relationship between the field, but here this is an auxiliary function, the vector magnetic potential, and the source. While the relationship between the field and the source does have a curl, which is hard to manipulate directly, this relationship is much straightforward, as we're going to see now. So now we reached our goal. We simplified, or we brought another form, another relationship between the source and the field, but here we are not bringing it directly. So we find it in two steps, and this is why it's called the auxiliary function. We first find A, then the curl of A will equal B. But there is an advantage for many problems. This relation here is very simple to solve, or for many cases, this relation here is like solvable, or like it can be solved easily, or more easier than the direct relationship between the curl of B and the source J. Here this is nabla square A, and this is a differential operator applied on a vector. It will produce a vector. We also, like you remember in electrostatic, we have this same operator, nabla square, but it was applied on the vector, the scalar vector potential function. So nabla square on a scalar produces a scalar, nabla square of a vector produces a vector. And the expression for nabla square of a scalar is different than nabla square of a vector. So we need to pay attention. Depending on the operand, the operator would have its own form. The easiest condition, or the easiest expression, is the Cartesian expression for nabla square of a vector. It's actually the nabla square of the scalar function ax in the direction ax, nabla square ay in the direction ay, nabla square az in the direction az. So now the left hand side is a vector, the right hand side also is a vector. Each side does have three components, and those will equal minus mu j. So j is a vector with three components, nabla square a is a vector with three components, so each component will equal, each component on the left will equal the component on the right. So this vector equation here can be decomposed or separated into three scalar equations. Now it's another level of simplicity. We are here required to solve just scalar equation. rather than solving a vectorial equation. And this formula here is solvable, and we can solve it by analogy. In electrostatic, we had this problem, nabla square V, where V is a scalar function, equal like some scalar quantity here on the left related to the source. Using the same, and like the solution for this were found to be this solution. V will equal the integration over the source for the source of electrostatic divided by R, and in the outside divided by 1 for epsilon naught. So this equation does have this solution. So we can say this equation will have the same form of the solution. Ax, the x component of the vector potential function, is related to the source component in x with this equation. Here it's mu naught divided by 4 pi. So this is the constant, and this integration is happening over all the source. And A does have the unit of Weber per meter. So, and this, we need to like know how to apply this form. The J here is the volumetric charge density, volumetric current density. Volumetric current density does have the units of ampere per meter square. Sometimes we have a surface current. Surface current density does have the units of ampere per meter. Sometimes we have just like a linear current, a current flowing in a wire, and it would have, so the same formula can be like converted to handle other forms of current. For surface current, the integration would be K, surface current density, multiplied by ds prime. For a wire current or a linear current, current flowing in a wire, the vector will be I. I here is a vector, which is actually sometimes we write it as I dl prime as a vector. So the vector here, either we put it with the I or we put it with the dl, is the direction of flow of the linear current. Also, like we can use this vector magnetic potential in solving problems for magnetic flux. So the magnetic flux equal B dot ds, B equal curl of A. So the flux will equal curl of A dot ds. From Stokes' theorem, this will equal A dot dl over the contour that is surrounding this open surface. And we remember that the contour and the surface are related by the right-hand side, right-hand rule. The contour is rotating in the direction of the fingers of the right hand, and the surface side is the open surface side is the side that is pointed to by the thumb of our right hand side. So this magnetic this vector magnetic potential is an auxiliary function that is heavily used in electromagnetics to simplify the solution of many problems, similar to the scalar vector potential V that's used to also like solve many problems in electrostatic. The law that I talked about in the beginning is the Biot-Savart law, and Biot-Savart law is based on this vector magnetic potential. We just said that A, the vector magnetic potential, is related to the linear current in that form, and here, like we are just expressing, as I said, the vector or the direction of flow of current, it can be like attached to the current itself, or it can be attached to dl. We know that B equal curl of A, so we can just apply the curl here. So this is an integration, and we have here a differentiation. This is a differential operator, but we can bring the differential operator on like inside the integration, because the operator here is applied on the general coordinate system, while the integration is with respect to the source coordinate system. So we have two different coordinate system, or like two different domains, the source domain and the observation domain. The curl here is at the observation domain. The integration here is on the source domain, so we can bring the curl inside the integration. There is an identity that we listed in 303, and also I think it's on the review slide, that is stating that when we apply the curl operator on a scalar function multiplied by a vector, this equal to the scalar function multiplied by the curl of the vector plus the gradient of the scalar function cross product the vector. As I said, the curl is a differential operator from the observation coordinate system when it's applied on the vector, which is something in the source domain. So it's two different things, two different domains. The curl will equal 0, the differentiation will equal 0, and we are left just with this term. With this term here, I is a scalar quantity and I here is constant, because we're dealing with DC current. The gradient of the 1 over r is a function of the observation domain. Curl of dl prime, which is a function or like something exists in the source domain. Okay, in Cartesian coordinate system, dl prime is, we'll handle this like 1 over r is the distance from observation point to from the source point to the observation point. So the distance between the observation point and the source point, x is observation minus x prime, anything prime is related to the source, square, so on and so forth, to the power of minus 1 over r. And just applying the gradient operator in the Cartesian coordinates, we'll find that the gradient of 1 over r will equal this expression, which is minus r as a vector from source to observation divided by the magnitude or the length of this vector cubed. So now Biot-Savart law can be expressed into this format for a wire current, a current flowing in a wire or a linear current. The magnetic flux density is related to the current I, which is flowing on dl, by this relation integrating over the, like here because it's source, like over the source, and here the source doesn't need, so it doesn't need to be like a closed loop. So let me correct this. So the Biot-Savart law can be written in this format: dl prime cross product with AR divided by R square, or dl prime cross product with R divided by R cubed. So we can like find dA for a differential element. So if we have a differential element that we put at the origin, and this element is like a linear current element, so it's IDL, dl in the direction of AZ, existing at the origin. The observation point is an arbitrary point, we can find the expression for dA. It will equal this expression here. So this is coming from this integration when we have just like a single element. So the integration is just the element. So A and dL are in the same direction. And for a differential element, this is the expression for the vector magnetic potential expressed in cylindrical coordinate system, because here this is a linear current which can be thought of as a very small cylinder located at the origin and the flowing current along the z-axis. So we have phi symmetry, and we can express the potential, the vector magnetic potential of this differential element in that format. Taking the curl, this would be the magnetic field intensity associated with this differential element, which is dH, and just doing the math will come up with this expression. It should be expected that the field must be closed loops along the phi direction, and the relation between which rotating in phi or rotating in the direction of minus phi, depending on the direction of flow. Here we are choosing the flow to be in the positive z direction, so the field produced will be along the a phi direction, which is the counterclockwise in this case. So here this is dA, and we can integrate dA to find A of the whole like linear current. There is like the integration would have this form, and then after finding A, we can just get the curl of A to find H, or we can start by dH and integrate. Also, like this term is integrable with this is a closed form integration for it. So after finding the integration, we'll have H. So either we integrate dH to find the total field generated by the line that's carrying current, or we calculate dA, the vector magnetic potential from differential element, and integrate to find the total vector magnetic potential. Once we had the total vector magnetic potential, we just apply the curl operator to find the total H. So we have so far studied 3 different ways to calculate the magnetic field caused by the current, which is the source of electrostatic field. The first one is Ampere's law. When we have symmetry, the B dot dl equal mu naught I, or curl of B equal mu naught J. We can find dB. We just had done the expression here for an element located at the origin. We find the magnetic field because of a differential element, integrate over the whole current path to find B, or we find dA, which is the vector magnetic potential because of a differential element. We integrate over the current source to find the total A. Once we found total A, the curl of A will equal B. So which one is easier depends on your experience, depends on the setup of the problem, but you can use whatever method of those 3 different methods to solve for the problem of finding the magnetic field because of some current distribution. So it's very important to practice and learn what each term in the Biot-Savart law means and how to express it. So I is the current. As we said, we are dealing with steady state current. dl is the length along the direction of flow of current. AR12 is the unit vector from source element to observation. 4 pi constant. R is the distance between the source and observation. If you look into this expression, you will find it close enough to the expression of the electric field generated by a buoyant source. So you will find that this is AR over R square, AR over R square, Q IDL 4 pi, 4 pi. So the relationship looks close enough. So there is some sort of like a similarity between static electric field and static magnetic field in terms of dependency on the direction, dependency on the distance, so on and so forth. Also, you can see there is some sort of like analogy between dV, the scalar vector potential, because of buoyant charge. The buoyant charge here is taking the form of a part of cylindrical charge distribution, and we compare it to the dA, the vector magnetic potential, because of infinitesimal cylindrical source. We'll find also like they are close in its form to one another, but this is a vector and this is a scalar. So when we have linear current, this is the expression or the integration to find A. When we have surface current, this is the integration to find A, and when we have volumetric current, this is the integration. So look to the difference, I dl, here K ds, here J dV. And because we regularly deal with volumetric current density, which is unit is ampere per meter square, and we frequently also deal with linear current, but the surface current is not that common in like dealing with. So here I just showing you what is the meaning of surface current density. Surface current, as the name like means, it's current flowing on the surface. So it's just, for example, like here, it's flowing in that direction, and its unit is ampere per meter. And in order to find the total current, for example, total current flowing in on this like sheet, you multiply by the width in the direction perpendicular to the flow of current. So here the total current I flowing into this section equals the width of the section B multiplied by the surface current density K. So I dl equal K ds equal J dV. And in all cases we integrate over all the source area. So when we have a closed loop, we just integrate over a closed loop. If we have like an open path or open contour, we integrate over the contour. In all cases, we integrate over all the source region. The most important thing is to understand the meaning of each element in the equation and learn how to express it. So here AR is like the vector from source element to observation point. DL is the vector along the flow of an infinitesimal current source. R is the distance between source and observation, so on and so forth. So here we would have our first example. In this example, we need to evaluate the magnetic field intensity on the y-axis because of a filament of current of infinite length on the z-axis. So we have a current on the z-axis from minus infinity to infinity, and we want to calculate the magnetic field at a point B on the y-axis. And here we're saying that when we find the field at this point, it means that we can find, or we already found, the magnetic field at any point on the XY plane. And I'm just asking you why. Why is that? Finding the magnetic field at arbitrary point on the y-axis, which means any point on the y-axis, means that we already found the magnetic field everywhere on the XY plane. Why? We need to think about this. So the answer for this is symmetry. We have phi symmetry. So this filament here, if we rotate it along the phi direction, nothing will change for this point. So if we rotate the XY axis like to any angle, so the XY plane will be the same. We just rotate the plane around the Z axis, nothing will change, which means this point, if we rotate, it can be, if we found this field at this point, it is the same as the field at this point with proper rotation, the same field as a point here with a proper rotation, because the difference between this point and any point on a circle in the XY plane with the radius rho is just the angle, and here we have phi symmetry, so the field shouldn't change for any point on this circle. And if we just found those so many circles, arbitrary radius rho, it means that we found the magnetic field everywhere on the XY plane. And also because we have Z symmetry, it means that we found the field everywhere, because the field at this point and the field at this point must have the same expression, because we have infinite extension here, we have infinite extension here. So finding the field at this point, or like arbitrary point on the y-axis, is equivalent to find the field everywhere. And this is because of the phi symmetry and the Z symmetry. And this example is on Biot-Savart law, and we need just to apply the Biot-Savart law. We have R, which is the distance from the source to the observation. So we choose arbitrary point on the source region, which is the Z-axis. We just take this point at height Z prime, and we need to calculate the distance from this point to the observation point, which equal R square plus Z square under the square root. The unit vector AR is from source to observation, so it is in that direction, which equal minus Z prime in the direction of AZ plus rho in the direction of A rho, and divide by the magnitude. So this is R and this is AR. DH, which is a contribution from differential element on the Z-axis, equal I dl. dl is in the direction of flow of the electric current, cross AR, which is from the differential source element to the observation point, divided by 4 pi R square, the distance from the differential element to the observation point. And here I'm just highlighting that correct problem formulation is a must. If you do the formulation wrongly, your solution will fail. So the first part is very important, and knowing how to apply the Biot-Savart law correctly. So you know what is DL, what is AR, what is R, and how to express each one of them. So DH will equal this expression here, and we have two components, a component in the direction of A rho and a component in the direction of Z. So this is for DH. Sorry, a component in the direction of AZ cross arrow, a component in the direction of AZ cross AZ. So let us continue. So the AZ cross AZ will cancel one another. So because they are in the same direction, and AZ cross A row will give us a vector in the A phi direction. And we should expect that because of symmetry. We should, from the beginning, we can conclude that the field must be in the A phi direction. And here we are integrating from minus infinity to infinity. And as I gave the integration, differentiation, integral differential pair for this expression early on in the lecture, we can just apply it. So the integration of this expression with respect to z prime, it's very important to define what is prime, what is not prime. Prime is anything related to the source distribution. So the solution would be this expression from minus infinity to infinity. Just applying it, the limits, will find h, which is I over 2 pi rho in the direction of A phi. This problem is much easier and shorter, solved using Ampere's law. We are here just experimenting the use of Biot-Savart law. And also, this is important to remember that same problem can be solved by more than one method, but the solution will be the same at the end, because each problem does have a single solution. Now we'll have a second example. In this example, we have just a filament of length 2L from minus L to plus L on the z-axis, and we want to find the magnetic flux density B at a point located R distance from the wire in the bisecting plane. Bisecting plane is the plane at the middle of the wire and perpendicular to the direction of the wire. So we need to solve this problem using two different methods. Method number one, by finding A, then find the magnetic field. Number two is by applying the Biot-Savart law and find B directly from the integration of dB. Again, there is a question which method is easier. We're gonna do that, see which method is easier after solving the two different ways. Again, I'm emphasizing many problems can be solved using more than one method, and we solve like this accordingly. We choose based on our experience and ability. We can decide which one is easier to solve. And of course, no need to say that the solution would be the same irrespective of which method that you choose. So the number one, we're going to solve it by finding A. So we know the relationship between A and I is that A equals the integration of dA, which is I over R. So here, if you remember, when we we did that earlier, let me bring this expression here. Yes, A equal mu naught I, so I dl over 4 pi R. R is the distance between the source and observation. A is in the same direction of dl. So we're just integrating over the source to find the vector magnetic potential in this way. So here we go. So it's mu naught I over 4 pi. The direction is AZ, and the integration of dl, which is dz prime here. So dl is in the direction of AZ, and its length is dz prime. R is the distance between source and observation, and this distance equals z prime square plus r square under the square root, and we integrate from minus L to L. Again, we also like give this differential integral pair expression early on the lecture. So this is A, it's equal to like just substituting the limits, we will find A, and it is in the direction of AZ. To find B, we just apply the divergence, the curl of A. And here again, finding the field at this point means that we found the field at any point on the xy plane. So the curl of a vector along the AZ does have this expression. We are working on the cylindrical coordinate system because this is the good or the best fit for the problem of wires. So we have this expression, and we can know that, or even like looking here, the differentiation with respect to phi is 0, because we should expect symmetry with respect to phi, and mathematically also there is no dependency on phi, so this term will vanish. We don't expect find a field in the AR direction, and we have a component in the phi direction. This also should be expected, that at this point the field, because of symmetry, must be in the xy plane, and because of the phi symmetry it should be in the phi direction, but mathematically it is shown without knowing this ahead. So integrating this with respect to r will give us this expression. And if you look into this carefully, for very long wire, when L is approaching infinity, or like L is much larger than R, and we do like the limitation, we like calculate the limitation, it will have this expression, because L square plus R square, we can just neglect the R square with respect to L. L will be cancelled out with L, and we are left with the expression we just calculated from the previous example. This is the case when L is much larger. So in the case of infinity, it would be like this expression. So this is the first method. Second method is applying Biot-Savart law. So we know the expression. We need the expression of R. We need the expression of AR. So here we are solving it with dl cross R divided by R cubed. So the expression of R is the square root of R square plus Z prime square, and cubed we have 3/2. dl is AZ dz prime cross product R, which is this expression. Z will cancel out with AZ, and we have a component in the A phi, and we just substituting this into the Biot-Savart law, we find the integration with respect to dp. Same thing here, we just apply the integration and substitute with the limit. We will get the expression for the field B, same as the expressions that we got using the first method. To say which method is easier, it depends on your decision. Whatever you feel more comfortable, you can use. But you need to learn that solving it with whatever method, you will get the same result in different steps. Next example, we need to find the magnetic field at the center of a square loop. So we have this loop and we need to find the magnetic flux density B at the center of this square loop. So we can benefit from this expression if we have this like filament of current flowing in that direction, and we can find the magnetic field at a distance r at the bisect. So think about this one, and we go here. So this one is similar. We have a filament and we have a point in the plane of bisect of this filament. So this filament and this point, they are the same as this filament and this point. We just need to map the length correctly and the direction correctly. So here, if you put the thumb of your right hand like along the z-axis, your right hand fingers will be rotating in the direction of the magnetic field. So we do the same here. Let us take this filament. We put the thumb of the right hand, like the thumb of the right hand along this direction, pointing in that direction. So the fingers of our right hand will be rotating in the direction of the magnetic field. So at this point, it will be pointing up, and we can calculate the value from this expression. And we go here, do the same thing for this filament. We'll find that also the field from this filament will be going up, same from this filament, same from this filament. And if you look to the geometry, because this is a square and this is the center of the square, you will find that all the components does have the same value, same amplitude, and it is in the same direction. So the solution would be 4 times the magnetic field generated by any single part of those, any single edge or arm of these 4 arms. So the expression would be in that direction, and we multiply by 4 and we get the solution for this problem. Another example here is that we have a circular current loop, the radius equal A. It is in the XY plane and it's carrying current I, rotating in the shown direction. In this, you need to like be able to express the direction of this current, and we need to find the magnetic field at any point on the z-axis. So we just choose arbitrary point on the z-axis, let us say at a height z0, and calculate the magnetic field. So we're going to use Biot-Savart law, IDL. So I is a constant, DL is we just take any segment of this loop, the length will equal A, the radius, multiplied by d phi. So it's IDL equal I, A d phi, and its direction is in the A phi direction. And this, all of this is like primed, because this are, or like those are the elements of the source. So AR is from this point to the observation point. So you can put the expression here equal minus A in the direction of AR plus Z0 in the direction of AZ. The distance is A square plus Z square. So AR, as I said, equal minus A, the radius, in the direction of minus AR. So radius A in the direction of minus AR plus Z naught in the direction of AZ divided by the distance. So we now formulated the problem. We just need to proceed. So this is IDL and this is AR, or sorry, this is R as a vector divided by R cubed as magnitude. Just substituting like A phi cross AZ, it will equal A rho, A phi cross A rho, it will equal minus AZ. With this minus, it would be plus AZ. So we'll have this expression here. We have two components, a component in the AR direction and a component in the AZ direction. We must notice that A rho is a varying direction unit vector. So A rho is changing from one point to the other. So in order to do this integration, we must express A rho in terms of constant direction unit vectors like the X and AY unit vectors of the Cartesian. So we just do this analysis. It would be cosine phi plus sine phi in the direction of AY. So here we'll have a component in this integration, a component in the direction of AX, a component in the direction of AY, a component in the direction of AZ. And for the AX component, it's the integration of cosine phi for one full cycle. Of course, it's equal to 0. Sine phi integrated over one full cycle, 2 pi, it's also 0. So the AY component will vanish, the AX component will vanish, and we just have the AZ component. Like doing the integration over the AZ component would give us this expression, which is showing us that the field will be in the AZ direction. So here there is no dependency on with respect to phi vanish. So here's the integration 2 pi is giving us just multiply by this area. So IA square in the direction of AZ multiplied by 2 pi. We didn't cancel out by and by for a reason that we're gonna know shortly. Okay, now we are introducing a concept that's called magnetic dipole. The magnetic dipole is any loop. Any loop can be considered as a magnetic dipole here. So like this loop can be triangular, can be square, can be rectangular, can be circular. Here we are solving the problem of a circular dipole. The radius of this loop is B, and the observation point is any arbitrary observation point that is in the far zone. So the distance from origin to the point of observation is much larger than the radius of this loop. So you can look here, we have symmetry in the phi direction, and as I said, we need to find the field at an arbitrary point. We decided to take the arbitrary point to be a point on the YZ plane. So this point mathematically or geometrically is not arbitrary, it is a special point because we choose the point to be in the YZ plane to simplify our solution. But I'm claiming that it is an arbitrary point. Why is that? Because the symmetry in phi. If this point rotated at any angle, if we take this plane, this triangle here, and rotated the solution will not change because we have phi symmetry. So if I find the field at this point, I can map it with the proper direction at any point on the same height and at any different angle because we have phi symmetry. But choosing the point here to be like on the ZY plane makes our derivation simpler. So we're gonna solve it by the vector magnetic potential. So A equals the integration of I dl prime over R. I dl prime equal I multiplied by B d phi prime. B d phi prime, and it is in the direction of A phi. This is the expression of IDL. R is the distance from the source to observation, which is the distance from this element to the observation. So let us put the expression for this R1 as a vector. It's equal to minus B A rho plus R AR. But the first one, B A rho, is in cylindrical, R is in spherical. So R1 equal, this is the R1 from observation, from source to observation, equal R, the position vector of the arbitrary point from origin to the observation point, minus B, the radius of the loop in the direction of A rho. So this R is spherical or whatever here, we can express it in whatever, but it is the position vector of the observation point, and this is in cylindrical. So here, A rho, as we said before, is not a constant direction. A phi is not a constant direction. So we must express them inside this integration in terms of constant direction unit vectors. So the constant direction unit vectors are the Cartesian coordinate system unit vectors. So A phi will be expressed in terms of x and y, and the expression here, like we did this many times before, so it's minus sine phi ax plus cosine phi ay. So the distance R1, we can also use the triangular equation, or like the triangular law of angle. So the angle here, we are talking about this triangle. This is the source, this is the origin, this is the observation. And we're gonna call this angle between the position vector and this radial ray as psi. So the length R1 here equal the square root of B square plus R square minus R multiplied by B multiplied by 2 cosine this angle psi. This is the we did this in 303. This is the cosine angle law for finding the triangle, the third arm. So it's R square, the first arm square, second arm square, minus 2, the multiplication of the two arms, cosine phi. So 1 over R equal this expression to the power of minus half. And we said that R is much larger than B. So doing that, we can neglect this term with respect to that term, and we are left with just this term. So we'll come to this very soon. The next thing to find is what is the value of cosine phi. phi is the angle between this vector, the position vector, and that vector, the radial vector. To find the cosine the angle, we need to multiply AR dot product with this unit vector, which is A rho. So AR here equals the unit vector along this direction, which is AR of spherical dot A rho of cylindrical. We can express this vector in terms of y and z. So this vector here would be this angle is theta, so it's sine theta in the direction of AY plus cosine theta in the direction of AZ. So sine theta in the AY, cosine theta in the AZ. This is the AR, and we already did this before for A rho. So it's cosine phi in the AX plus sine phi prime in the AY. Remember, this is primes and this is unprimed. So the Z component is perpendicular to both. It's going to cancel out. The only thing remaining is the AY component. So the cosine psi equal sine theta sine phi prime. So the expression here for 1 over AR, we just substituted cosine psi with sine theta sine phi prime. And we can use Taylor series expansion for this term. So this term will cancel out, and the remaining term will be multiplied by the power. So minus half multiplied by minus 2, it would be plus 1. So this is, roughly speaking, equal 1 over r multiplied by 1 plus b over r sine theta sine phi prime. So the integration now is that, and A is in the direction of A phi, and doing this integration, we will have here, so this is 1 over r, just substituting A phi with the expressions and doing the math, we'll find out that the remaining part is just the sine theta, and we'll have like this expression for the vector magnetic potential. So the sine cosine term will cancel out, and the sine phi square is the one that is remaining, and it will produce the expression shown here. So just doing the math, we can come back to the problem formulation. Remember the circular independency. When we solved this problem, we found that the direction of the field is in the minus AX, which is that direction. But as I said, if we rotate this plane, we'll have the same thing, and because of the circular symmetry and the direction of the field here, minus AX, it's actually, when we rotate, we'll find that this is actually the expression of A phi expressed at this point. So it's here, just at this point, it's minus AX, but when we rotate, we'll find this actually is the expression of A phi. So A is in the direction of A phi, as we should expect it from the beginning, because A is in the direction of I. And here we just organized the terms to be I multiplied by B squared, which is the area of the loop. So this is why in this equation here we keep it like by A squared, the area of the loop. because it's needed for the definition of magnetic dipole. Okay, so the solution here equal mu naught I multiplied by area sine theta in the direction of a phi divided by 4 pi r square. So this is the expression for the vector magnetic potential because of a small circular loop placed in the xy plane with the center at the origin. So now we have A expressed in the terms of a phi. We can use spherical coordinates. Why? Because it's more suitable for an arbitrary point, and we can find the magnetic flux density by just calculating the curl of A, and we will have this expression for the magnetic flux density of a magnetic dipole. And we keep this as one term always. This is the magnetic dipole momentum. We just here like bringing to your attention that this magnetic dipole moment I multiplied by the area is called M, and we can just express A, the vector magnetic potential, to equal M, which is in the direction of flow of the current. Sorry, we'll talk about M shortly. Multiply cross product with AR, which is the direction to the observation point. So here this is the dipole moment, and the direction of this dipole moment is like normal to the loop according to the right hand side rule. So you rotate your fingers in the direction of current, your thumb will be pointing to the direction of this magnetic moment, which is in our case the AZ direction. So A phi equal AZ cross AR. AR is the direction from the origin or the center of the loop towards the observation point. So this is the vector magnetic potential of this small circular loop. The magnetic flux density caused by this magnetic dipole does have this expression here. So this solution here for small circular loop, if this circular loop is like a square or a triangle or like a rectangular loop, but it is also small, with some proper approximation, we can find out it is the same value. So the same moment, if the square loop does have the same moment as the circular loop, their effect or their field would be approximately the same. So here, if we have a magnetic dipole and we have a cross section, so the loop is circulating like this, goes out of the screen, in, out. So like this is the loop. We have a cross section, and this is the like electric dipole. You can see that away from the, like in the far field, away from the loop or away from the dipole, the magnetic fields of the magnetic dipole looks very similar to the electric field of the electric dipole. Look to the magnetic field here, it's very similar to the electric field here. So this is an electric dipole with those lines, electric field lines. This is a magnetic dipole with those lines, magnetic field lines. Far from, or like away from the dipole, the field lines does have the same shape, and they have like similar expressions as well. Another example. Here we're just like working over and over on the application of Biot-Savart law, so that you get like to a very good level, solving or using it. So here we have like a filament along the Z axis, but it is not centered at the origin. It is just at two arbitrary points, Z1 and Z2, and we need to find the field at any point on the XY plane. So again, writing the Biot-Savart law, we did this before. Can choose the point to be any arbitrary point or a point on the y-axis, then map the field because of the phi symmetry. But here we're solving it on taking any point on the XY plane. So IDL cross product with AR, we did the AR before, it's equal to minus rho in the A row minus Z at the AZ. So we just take any small element here and we are integrating from Z1 to Z2. The distance between a point here is Z square plus rho square. So this is the expression. We just do the math. I want everyone to do the math of this problem and prove that the field does have this expression here. Alpha 2 is the angle that's pointing to Z2. Alpha 1 is the angle pointing to Z1. So you need to do this yourself and prove this expression here. It's a very good exercise for you. We have homework number 2 that is due in a week from our discussion session. And again, as usual, at the end of each lecture, we have the learning objectives. I want every student to read those points and make sure that those points is clear in his mind and he understand what is given in these points. Thanks for watching the video and meet you in the discussion session. Assalamu alaikum.